Let the help begin. I will foolishly attempt to be my own cameraman person. Yeah, it's fine though.
Back and forth when he's gonna move forward.
It's all good. I think it's good. I think it's okay. So you had a question about number 27. Now I've heard horror stories about number 27 from some good students. Yeah, 37. This is number 7, right? In Fisher, on page, what is it? 204. A little bit off. Now, so I think I think the logical trap that I have been lured into personally is it's very different to suppose that the real axis is mapped to itself as opposed to, say, pick a particular point on the real axis and map it to another particular point, right? Like, that maps the real axis to itself in a very specific way, and I'm worried that if I do that, then maybe I'm removing a flexibility in the solution which I might need in order to fit the other data. So I think that's something I need to be wary of. That said, I think problem A, I think we can just write that down. So like t of 0 equals to 0, that says to me that t of z has a z in the numerator. All right. T of I equal to infinity, that says to me that there is a z minus I in the denominator. So that formula already has, that formula as it stands does what? It does this and it does that, right? And so I just need, there's still a flexibility. Fractional linear transformations still have 1 degree of freedom left. There's our choice of the multiplier, right? And so we can figure out what A is by just plugging in the other thing. T of 1, which is 1 over 1 minus I, times A is equal to 1, right? So therefore, A is equal to 1 minus I. Oh, therefore A is equal to 1 minus I. Yeah? So we have T of Z is 1 minus I times Z divided by Z minus I. Please tell me that's the answer in the back of the book. Is that the answer in the book too? Or you don't care? Okay. I mean, I have confidence in my work. I don't need to check the answer in the back of the book. I will accept.
Yeah, the one that I got a different answer was for part B. I had something that was different in the back of the book, but from what I can tell, when I plug this stuff in, it still works.
All right, so let me, now that we have put those in frame, I'm going to zoom in a little bit more. Actually, so I'm just writing in the middle board. I'll just copy the problem down again. I just need it. All right, so part B, let's see here. We want the reals to map to the reals. But that doesn't say that, I'm not saying that everything has to be fixed, obviously. Goodness. I don't know how to think about that, honestly. So what I want t of the real line to map to the real line, I hope. And I want t of the imaginary axis to map to this circle. So
this one wasn't as bad because the point 0, 0 stayed the same because the circle was centered at 1/2, but had a radius of 1/2, I think, if I drew it right.
So okay, let me draw a picture here. That's a good idea. So where's that circle?
I think it's centered at 1/2.
1/2. It's got radius of 1/2. It's this circle, right?
Yeah, I think so. So then you can I did 0 to 0.
So the thinking is, let me call this, the imaginary axis. It's wrapping around this circle under the map, yeah. And so you're thinking that.
So I just kind of like wrapped it around, so then made T of infinity 1.
Wrapped it around, so and this maps to that.
Yeah, I don't know if this still works. Like it seems like the steps worked, but mine was just a little bit different than what the book had. So then saying like T of infinity is 1 takes like that end and brings it to the opposite side of the circle, kind of. Am I like thinking?
Say T of what?
Infinity equals 1.
T of infinity equals 1 is what your thinking was. T of infinity.
And T of 0, 0, and then the third point I feel like is kind of arbitrary, but
Third point is arbitrary.
like something on the real to something on the real spectrum.
Well, tell you what, let me just take a somewhat scary and calculationally onerous step back and say that we're looking for ABCD, right? Subject to, what's the rules? AD minus BC not equal to 0. We know that. I mean, whatever our choice is, that has to be case. And in this case, we're looking for t of a real number, let's say x, because we like x to be a real number. Or we could use r. We want that to be equal to ax plus b over cx plus d. We need for this to be real. So whatever I choose for a, b, c, d, that has to be a real number. I mean, that's what it means for the real axis to be fixed. So that's something we have to work with. I don't have a good intuition for how to work with that right off the top of my head, but that's data that we have. Now you want to look at the circle, I think, and I think that's a good idea. Now you said t of 0 is 0. That's a choice we could make. I guess the question I'm kind of lost on is, and maybe I'm just missing, because there's lots about fractional linear transformations that I don't know. All right, like I don't appreciate deeply the things about symmetry and chordal distance and that stuff, and maybe understanding some of that would make this trivial, because there are, some geometric things there that maybe could be applicable here. I don't know. But you want to wrap the circle in such a way that it fixes the real axis. So sending 0 to 0, that's a start. Sending 1 to 1.
I said -1 to -1.
-1 to -1. -1 to -1. Why would you do that?
Because it's on the real axis and then it's still on the real axis.
Oh, so that's just a choice.
Yeah.
Yeah. But I'm thinking, I guess my mind is drawn to, if this may be too greedy, but if I map that 1 to 1, would that work for me? Can I try? Let me try this for a second here. So it's t of 0, 0. T of 1 is 1. And if I wanted to go to this circle, I guess I should do. That's the thing, is I don't know. I have no earthly idea where I should get the third point on the circle. Maybe that's why this doesn't work. I mean, I shouldn't have erased what you told me. Sorry.
So if it was 1 instead, then
Oh, but this is,
then my A would be 0.
if I can do this and see where it takes me, right? Let me do this, see where it takes me, and see if that pins it down. Because the other thing I know is that I know that t of iy, right, is equal to, well, it's equal to aiy plus b over ciy plus d. And I know that that's equal to w such that what? Such that the norm of w minus 1/2 is equal to 1/2. Oh. Yeah, see, if I was a student in this course, I would have written those down, and I would have tried to face those equations directly.
It's really hard, I tried.
You tried? Okay.
Well, I tried doing the cross.
How did you look at it being real? How did you look at being real, though? What equation did you study for it being real? See,
No, I was trying like the cross ratio, and that was nothing like.
well, but to make the cross ratio work, we need 3 points, right? And I don't know what 3 points. It's not clear to me how to pick the 3 points here at all.
Does it matter? And you just do it however you want.
How would you do
As
it?
long as it works.
Okay. If it works, it works, right? What are your 3 points?
So like I did t of 0 is 0.
Uh-huh.
T of minus 1 is minus 1.
T of minus 1 is minus 1, okay.
And then t of infinity is 1.
T of infinity is 1. All right, so I can write down that's T of z equals to z over z minus 1 times some constant, let's call it a, no relation, and, well, maybe some relation, I don't know. And so we need that T of minus 1, which is equal to minus 1 over minus 2, a, is equal to minus 1. Therefore,
How did you get that minus 1 on the bottom?
oh, hey. Wait a minute. Wait a minute.
T of infinity is 1.
Ow.
Z would be.
Curses. T of infinity is 1. You're right. I don't know.
The way that I had it was Z
Oh.
over Z plus A.
Yeah, I think that's you're right. You're right, Bethany. I should say plus a. I'm sorry. I was juxtaposing the
Yeah. But I think you'll get the same thing actually.
So that's funny. So that would give me. That's actually very, to quote Dr. Wayne, ironical. Let's see. Minus 1 over, and that would be equal to minus 1 again. Oh, so many minus 1s. So minus 1 is equal to 1 minus a. Therefore, a is equal to 2. So you get T of z is equal to z over z plus 2. Now that is not the answer in the back of the book, you say. And the question is it legitimate? Is that a legitimate answer? I mean, you've mapped 0 to 0. You've mapped minus 1 to minus 1. You've mapped infinity to 1.
So like I tried, I plugged in like 1/2 plus 1/2.
Now, if I think about this, let me put just a second. So let me put these in order. Yeah. So in order. In order, we have minus 1, 0, and let's say infinity over here. Yeah. And if I do them in that order, then or wait, how I should. Sorry. Yeah, like this, yeah. Then the corresponding points, so you did minus 1. Wait, oh, but they're not on the circle.
Yeah, that's a problem. I was thinking of
Oh.
infinity as infinity on the imaginary axis.
Well, I think that should be I infinity
Yeah.
in this. Well, I'm a little bit. You're getting to the edge of where I'm not sure what I'm saying. But this, I think you can quickly see that this will not work for taking the reals to. Will this take the reals to the reals? Even? If I put. Oh yeah. If I put z as real, I get x over x plus 2. Is that real? Yeah. So you do map reals to reals. Do you map imaginaries to? I think if you look at the imaginary though, you don't get the circle. Is my point. Yeah. I don't think
I'm
anyway.
assuming
IY, so that's IY over IY plus 2, you know? And if we set that equal to W, and calculate the magnitude of W minus a half, what's that give us? You're like, a mess? Well, okay, so that's IY times 2 minus IY over 4 plus Y squared minus 1 half, which is like giving me a headache. Oy, oy, oy. Y squared plus 2IY over 4 plus Y squared minus 1 half. I should at least make a common denominator before I give up on it. Y squared plus 2IY minus 2 minus 1 half Y squared divided by 4 plus Y squared. Which is not going to have magnitude a half. Yeah. So it's not on the circle. But you already knew this. So you think we could modify your solution by thinking about sending I infinity to 1, maybe?
I don't really know what that means necessarily, but it's a number.
What's that? Oh, it's 8. Yeah, I don't either. I mean, that's the thing, is the infinity we're using here, there's not different. This is exactly the issue I was talking about. The infinity that we use in certain things, like to denote a deleted set, that is a different notion. We're just using that as a notation to delete an infinite ray. We are not, in that context, identifying all the points in all different directions at infinity as the same point. But that's what we're doing with the extended complex plane, is we're adjoining a point at infinity, and we're thinking of those all as the same point, which means I can't distinguish I infinity from infinity. They're just infinity.
I think maybe something else I'm doing
Yeah.
is mapping I to like 1 half 1 plus I. So like something on there going to like the top of that circle.
So this is 1 half. And then,
1 plus I maybe.
oh, okay, yeah. Sure. Well, I'll just say at the moment, I do not know I do not know a fast way to do this problem. So, I mean, A, perfectly reasonable test question. B would be mean. Yeah. Unless when I write my solution, something clicks. You know, in which case I would make an announcement and say, hey, I saw the light. You know, you can pray I don't see the light. Yeah.
How do you get T of Z?
Up here?
On like down for this one. It's always Z over Z plus to the part B. How do you get T of Z equals C over Z plus A?
Oh, this was, it's not true. But we were, Bethany was thinking that if we mapped infinity to 1, that would be helpful. And so if we want infinity to map to 1, we need, when we plug in the coefficients, when we plug in infinity, we basically need to get like infinity over infinity. But there's still a residual freedom, so we just added a in the denominator.
Is that so? How did
And we were forced to put, we already had a z in the numerator because we're mapping 0 to 0, which puts a z up here. So the only residual freedom was just to add a constant down there. I can't multiply by z anything, but I can't put anything here but 1. Otherwise, when I plug in infinity, I'd have like, you know, leading coefficient, essentially, infinity over whatever number times infinity. That wouldn't be 1. That said, this doesn't solve the problem. I mean, it's a neat idea. It's good.
Can you go over how you got T of Z up there real quick?
Yeah.
I know T of 0 equals
Yeah, so in the previous one, I put z up top because we're mapping 0 to 0. I put z minus I in the denominator because we wanted t of I to be infinity. Then the middle one, t of 1 equals to 1, I know that I can fit that by the appropriate choice of the multiplier a. That's the only freedom I have left in the selection of the fractional linear transformation. So I think I'm not sure I'm going to have much more to tell you about B, C, or D here either. I think it's kind of the same trouble.
How do you like figure out?
I mean, I can-
mapping to what is, like,
I
the
can-
right-
I can try to cheat and look at Jonathan's solution, see what I find here, but
I mean, I'm just like I don't understand how like the ones that don't specifically. I know they're like giving you something to map to, but like the one we were just doing, like how you pick like t of whatever maps to something. I don't know. Is that just like trial and error? You should like start picking stuff, or is there like a right
no, there's got to be something more. Let us steal from Jonathan. So for part B, he says this. The real axis maps onto itself and the imaginary axis onto the circle. Solution. We are mapping a line to a circle. We can expect this map to be some sort of inversion. A line to a circle. We can expect this map to be some kind of inversion. Okay, that's kind of intuitive. So t of z should be something similar to 1 over z. Any kind of inversion, infinity goes to 0. So we know that the imaginary axis, the infinity on the imaginary axis should map to 0. And since infinity and 0 must map to opposite sides of circles, this implies 0 maps to 1. So he says consider the map t of z is 1 over z plus 1. Here t of infinity is 0. T of 0 is 1. Now t of I is that. So I feel like this solution has been created by looking at the answer in the back of the book and adding some.
I think that some reverse engineering
I believe reverse engineering may have been used in the production of this answer, and I respect that. Sorry to grade your homework in the review session, Jonathan. I'm only looking at it because I recognize its quality. Well, anyway, let's not eat our time up talking about this. I think we'd be better served talking about the other things. Because I'll try to figure out something intelligent to say about it tonight, if I can. If I can't, I may just throw my hands up in disgust and agree that I need to make sure I ask you problems where the choice of the points defining the FLT is at least somewhat natural.
Is there like a way that you go about like picking the points, or is like 0, 1, and I like a...
That's the thing I don't know. I don't know how to pick the points. And that may not even be the right idea. Yeah, look at what? 36. Now that, yes. That I actually have a solution for we can look at. What was it? Is that the third power one, right? It's like Ah, wrong place. Where did I put that thing? Very annoying. Where did I put this thing? I was just looking at it and then I stupidly closed my files. Come on. Goodness gracious. Where is it? So, I said problem 28 of mission 3 from 2015. I'm in the wrong year, aren't I? What mission did I say? 4? Here we go. Well, I found problem 38. Haha. Oh, here we go. All right. So this is the problem I've assigned you guys. Now, this needs some editing because, unfortunately, I defined the arg sub alpha to be slightly different. Annoyingly, in this year, I have deleted the other side of, like, arg alpha actually does match up with the principal argument in this because I have defined it so that it includes the upper. All right, anyway. So what's your question about this one? Before I mean, I can just, want me to just wander through the solution and see if we can identify the answer to your question or your question?
Yeah, so I guess like the principal third root, if that's what you would call it.
Principal third root of unity, yeah?
Yes. That doesn't work because that goes from minus pi over 3 to pi over 3, right? In this situation.
Right, yeah, so.
Then we want the one that's just shifted up.
Now, the principal third root of unity will work on half of what you're interested in.
So, like, but what we want
Right.
is basically like arg sub 0, right?
I'm not sure it is, I mean, I don't know right offhand. I have to get everything back out on the table for myself before I can offer an opinion on that. There's a lot of moving pieces in this problem, yeah? So I'm trying to find the inverse to the cube function restricted to this sector, right? And so the thing to notice, of course, is that when we cube that, we get the deleted complex, well, the Pac-Man plane. He's chopped down, but he's lost an eye too. But that's the positive slit complex plane. And let's see, what do I got? So I'm just here, I think this math, I'm just establishing that this picture's, legitimate, right? Now Sam tried to get me to fill in that dotted line. I think it's because he wanted to use. I think I know why. All right, so I think I know why actually. Anyway, what am I getting to here? So I'm working out that the inverse should be the cube root of the modulus times the exponential of I over 3 arg tilde sub naught of w, where in my current language, which I need to fix, sorry I haven't had a chance to fix before I talk to you guys, but this arg tilde naught of w is the angle between what and what?
So for the picture up in the top, are you saying that instead of removing the slit on the positive real axis, we're removing the slit on the negative real axis based on the way you defined it?
I don't think I'm saying that. I mean, I think that this is the same problem you're given, right? The angle 2 pi over 3 is deleted, angle 0 is included, right? And when we cube that, that gives us the positive slit complex plane, C+, right? And then what I'm saying is that, so the range of this half open sector, if you will, right, is the C+, right? And so the explicit inverse function is given by this. F inverse of W, it's the cube root of the ordinary garden variety real cube root of the modulus of W, and then exponential of I over 3 times the argument. And I say arg tilde sub naught, but honestly, for us, that's just arg naught, because we have defined arg naught to be include 0, right? See? So you see right here, this is exactly, so good, yeah. And this is trash. That's just a mistake. That doesn't make sense. Because arg w is between minus pi and pi included this year as well. This is just an error, which I will fix as I write up my solution until the wee hours of this morning. I foresee this happening if I don't fall asleep, which is also very likely. So I guess I'm going to be writing the solution to this mission like all of Saturday. This thing is going to take me forever. Like, hey, you signed it to us. It's your fault. It's true. Fair enough. You got me.
This makes sense.
Oh, good. So so this is the domain for the principal third root, right? And so the principal third root, when we cube it, its image of the standard domain of the principal third root, it's the C minus, right? And so we can compare these local inverses on the intersection of their domains. And the intersection of their domains is just, in this picture, it's just this part, right? I think. How do I get this? I don't follow. Whoa. What on earth? I really don't get this. Why do I say that the domain of the inverse functions intersected is the union of D1 and D2? Maybe I'm missing something here. Let me zoom back out a little bit. Oh, the domain of the inverse functions, though, right? The inverse functions, their domain is what? The one inverse function has domain C minus, right? The usual, the principal third root. No, wait a minute. Excuse me. The principal third root of unity is the local inverse for the cube function with respect to the sector between minus pi over 3 and pi over 3. Right. Its range is C minus. C minus is thus the natural domain of the principal cube root. On the other hand, C plus is the domain of our local inverse, which I've called G or whatever here, right? So what's the intersection of C minus and C plus? It's a disconnected set, right? There's above and there's below the real axis. That's my next point. It's for the inverse functions, the intersection of the domains of the inverse function, it involves the upper and lower half planes, which I'm calling D1 and D2 here, right? So D1 imaginary positive, D2 imaginary negative, and so you can compare the inverse functions, how they behave on these two. You can compare how the inverse functions behave on these two regions separately, right? The story is different on D1 than it is on D2. On D1, what do I have here? So I'm just rewriting what the inverse function is. Here's the principal cube root. This is my non-standard third root. Yeah. Angles between 0 and pi, angles between minus pi and pi. So what I come to the conclusion is that they match. They're equal on the upper half plane. So these different local inverses on the intersection of their domains in the upper half plane, they match. However, if we look at the lower half plane, they do not match. They have genuinely different values on the lower half plane. And on the lower half plane, I work out that in fact, the non-standard third root of third root function is actually equal to 2 pi over 3 times the third root function of w. So that's it. I mean, when you compare them on the intersection of their respective domains, they either match on the one connected component or they're related by multiplication by a principal third root of unity on the other. That's it. And that's not surprising because if we look at any two branches of z to the n, right, any two local inverses, the inverse has to be, like the formula for the inverse has to be chosen from the nth roots of z. There are n choices for that. And those n choices are related by multiplication by the nth roots of unity. So this result is not surprising. And it would be general. Like generally, if we looked at the nth roots of w, we've got the principal nth root, and then the principal nth root of unity times the nth root, the principal nth root of unity squared times the nth root, and so forth. Like this is the nth roots of unity for nth roots of w. This is the standard nth root of unity function. These are other possible local inverses, which, I mean, the thing that's kind of perverse about this particular, anyway, I don't want to say much more. I'm just going to make it more confusing, so I'll shut up. So I think that's a tough problem. I just think it's a worthwhile thing to struggle through because you guys have not thought long and hard about local inverses yet, yeah? And it's tricky. I do think it is tricky. I hope I haven't made it more tricky than it needs to be. Now you asked me about problem 30 what? 39. Let me go back to that one. So this is problem 38. Was this? But this is the one you asked me.
38 is more.
Oh.
39.
This is the other. This is the proper version of 38. All right, but you want to talk about 39, so I'll try to do that. So here we have 1. So you want 1 on one side and minus 1 on the other, right? And a solution to Laplace's equation. I think that's this. This was the other problem I have. That's not the one I assigned you guys. I thought it was too easy. Kidding. I don't want to assign, like, I don't want all of your homework to be solving Laplace's equation with boundary values, right? That's one thing we're doing, it's not everything we're doing. So here's the solution to that one. So the idea is to find a mapping from the circle, from the disk, to this half plane. Yeah, it's just 39, I think. Yeah, phi of 1 is, I want 1 and minus 1, either on the left or the right part of the circle, yeah. So my idea was that if I could map one half of the circle to the upper imaginary axis and the other half to the lower imaginary axis, then I could easily solve Laplace's equation over here using the appropriate angle function. So like over here, if I want an angle function that works on this half plane, the plain old inverse tangent works pretty nicely. Like inverse tangent of v over u is defined over here for u positive, and it'll give me a value of pi over 2 as we approach there, and minus pi over 2 as we approach down there. So if I multiply it by 2 over pi, the inverse tangent goes to 1 up here, and it goes to minus 1 down there. But then I just need to find the fractional linear transformation that takes me from this circle to that line. And I know some things, like I want the jump in the angles, right? I want the jump in the boundary conditions needs to map to the jump in the boundary conditions. Like that's very guiding. That was missing from like B, C, and D over there. That kind of feature. Shut up. So my thought was that I should orient it, and so go from 1 to I to minus 1, and that will put the left of the inside of the circle, right? I need to map those to points which put as we walk along the boundary, the right half plane to be on the left. So I'm going to map, I think, what do I do here? I map I to 0, because that's where my discontinuity going from 1 to minus 1 in the solution goes. So I map the I to the 0. I mapped the 1 to the I believe. And I think I mapped minus 1 to minus I. And I think my reasoning for why that should be was just symmetry. You could reasonably, I think, have mapped minus I to infinity. Oh, yeah, and that's right, and that's just, I don't know why I chose to make the vertical half plane. I mean, that was just a choice, but you could have done the upper half plane. That's fine. Yeah. If you happen to have the solution to Laplace's equation on a disk with 1 on the upper edge and minus 1 on the lower edge, you could just take that and multiply by I in the argument. You could just rotate the argument by 90 degrees. I think we actually have solved that problem. So we could take the problem we already solved and just rotate our arguments by 90 degrees. That would be like a much lazier way of doing this problem. Not the way I wanted you to do it, but a way. So does that start to make sense? And so once you have figured out I is going to 0, then that puts z minus I in the numerator. And I'm not. So you notice here, I didn't in my mind when I wrote the solution, I didn't see what to do with infinity. But if I had chose infinity as one of my points, this made this so much easier, because then I would have known that I want f of infinity. F of minus I to map to infinity. Because in some sense, this point and those points down there are joined at infinity in this extended complex plane, and that's where we jump from the pi over 2 to the minus pi over 2 in the argument function is the idea. But unfortunately, I didn't, so I have f of 1 is I and f of minus 1 is I, so I got 2 equations and 2 unknowns, and I had to solve them, which isn't a big deal. But you can, it's much nicer if you can see what to do with infinity.
So you're solving for A and B.
Solving for. And as you can see, after the dust settles, I end up with basically a z plus I in the denominator, which reflects what Bethany was saying, which is that, well, I guess she wasn't saying that because she used a different map, but, well, no, she used a different plane, but the same idea, half plane. And so you can see that this map does send minus I to infinity. If we put minus I in here, we get division by 0. It's mapping to infinity. Anyway, there's my fractional linear transformation. And so I'm like, okay, well then 2 over pi times arg w, that solves in the half plane with a 1 on the upper imaginary axis and a minus 1 on the lower imaginary axis. So then I use the conformal mapping theorem, which says that I can steal the solution in the w plane back to the z plane by just composing the w solution with the map.
It's a little bit different because I had more things inside the argument, but then I had a minus 1 on the outside. Is that
I don't know.
like that? I plugged in things to see if it worked, and it did.
It worked okay, yeah.
But like it's okay to have a plus b, right?
Oh, so you got like a plus pi?
So I had 2 over pi times the argument of that, but then I also on the top had multiplied by minus 1 plus I, and on the bottom minus 1 minus I.
Huh.
And then completely separate from that term, minus 1.
Huh. I bet the numbers you have inside the fraction simplify to like a minus. And or something like that. I bet those when you what numbers do you have again?
Inside the argument.
What were the multiplying numbers?
Minus 1 plus I on the top, and then on the bottom, minus 1 minus I.
All right, let's simplify that. So your solution is my solution, like,
Oh, because I did it.
well, your solution is my solution rotated this way, clockwise 90 degrees. Makes perfect sense. They're the same solution. Geometrically, we can see it. Yeah. Now, that's actually what the gory details look like. I mean, this is the XY solution in real notation. That satisfies that. So,
Do we have to put it in XY notation?
probably not, but I'd probably give you like bonus points if you did. I mean, you got an hour test, so I mean, if you're stuck on everything else, and just this thing is still lingering. Do you guys have other questions? Number 40, yeah, okay.
But like for the homework reason,
No, that's okay. I've got too many things open. I hope my review makes sense to you guys. I tried to blather on long enough that it wouldn't be mysterious. My apology for all the like paragraphs you read that basically end with "and so this doesn't matter."
But I like to hear that.
It's like keep reading for the punchline. That's here. So, thank you, Bethany. So problem. So the cross ratio, I want you to know about the cross ratio for your just like general knowledge. But when I think about an hour test, the thing we're doing, trying to see where infinity goes and where, what maps to 0 if possible, and then one other constant to fix the FLT, that makes a much more reasonable kind of question for a test sometimes. And I'm not saying the cross ratio won't be there. I'm just saying it's very likely that I test on something that just involves this, once you map to 0 and you know where what's mapping to infinity, that allows you to build the formula step by step. And if I'm going to ask a question that involves explicit computation, that's a better kind of thing to ask about than if I ask a question that's step 1 is to solve the cross ratio, and then to do analysis past that. That's just a lose-lose for me grading, because most of you are not going to get past the cross ratio. So the cross ratio is kind of a question that stands on its own. Like, here's 3 points, here's 3 points, find the thing. So this one, you wonder about A? Do you wonder about A? The whole thing? Okay, so like part A, I'm just saying we have the complex exponential. Well, the hyperbolic exponential, which is e to the z. In the case of hyperbolic at z, that's e to the x cos y plus j e to the x sinh y. You're not expected to memorize this. I would give it to you if it came up, okay? So here j squared is equal to 1. And we do have the abstract algebra help session in here. Oh, okay. I don't want to give, there's some confusion about when the help session is. So I want to make it clear, like the complex help session is just about to finish, which is okay.
Oh, no, I'm not, I'm just here to finish your homework.
Very good. That's fine. So, okay, good. Okay, so part A, let me help you with. So we're trying to, basically, what's the problem of finding the inverse function? You're trying to say w equals e to the z, right? So if this is f of z, yeah, then f inverse of w is equal to z. All right? So in other words, what we have to do is we simply have to, and z is equal to x plus jy. So all I have to do is try to solve this. So I need some letters. So w is u plus jv, e to the x cos y plus j e to the x sinh y. Yeah? My goal is to solve that equation for x and y. That's what I got to do. Now, that's a hyperbolic equation, which means we can look at the real and the imaginary part, or the unreal part, and those give us two separate equations to look at, right? So we get v is equal to e to the x sinh y from the j component, and from the component with 1, we get u is equal to e to the x cos y. And then the question is, what games can you play with those equations to eliminate either y or x to get just an equation involving one or the other? So do you have an idea? How would you eliminate, how would you eliminate x? Well, we can't pick, we need to work it for arbitrary x and y. We don't want to do that. But oh, are you saying, I mean, we could solve both for, I guess we could solve both for e to the x if you wanted. Would that make sense? So like the first one gives me e to the x equals to, what is it, v over sinh y, yeah? And this says e to the x equals to u over cos y. So what's that give us? V over sinh equals u over cos, which we can put y on one side. That says that the hyperbolic tangent of y is equal to v over u. But hyperbolic tangent is an invertible function. It has a well-known inverse hyperbolic tangent, or arc hyperbolic tangent. We just found y. So y is equal to inverse hyperbolic tangent of v over u. Now, we need to do some kind of similar algebraic stuff to eliminate y. So when I see equations like this and I think about eliminating y, and if I've got Cauchys and Cinches and I'm trying to eliminate something with the variable in their argument, the thing I always use, it's like when I have cosines and sines and I'm trying to eliminate, if I've got cosine theta, sine theta, I'm trying to eliminate theta, I always think about cosine squared plus sine squared, theta equal to 1, because that allows me to eliminate the theta. In the same way, if I've got Cauchys and Cinches, I think about like cosh squared y minus sinh squared y. That's equal to 1. So that's that identity on the, you see what that has? On the left-hand side, it's got y. On the right-hand side, it's got no y. That eliminates y is what that does. Take that, multiply by e to the x squared. What's that give us? So then you got to remember, where we started. See, we had v is that, right? U is that. And the reason I multiply by e to the x squared is to make those turn into u's and v's. That's why I did that. Uh-huh. Exactly. So now we've got u squared minus v squared equals e to the 2x, which is very nice because now it's an equation just with x, and u and v we can solve for x. Take the natural log of both sides, right? Which gives me 2x, right? And there you go. X is 1/2 natural log of u squared minus v squared. And so we find that the inverse function of u plus jv is apparently equal to 1/2 the natural log of u squared minus v squared plus j times the inverse hyperbolic tangent of v over u, which I find deeply satisfying because if we look at the inverse function, well, if we look at the inverse function for the imaginary exponential, not this is bad notation. Stupid notation. If I say h of z equals to e to the z, yeah, then the inverse, a local inverse for the exponential is given by the natural log of, the square root of x squared plus y squared plus I times the inverse tangent of y over x. Now that's not, for appropriate, in a certain region, that's the inverse. That's a local inverse, but look at how it's just the, this, we can pull the half out, yeah? So there's a very strong analogy going on here between the complex numbers and the hyperbolic numbers. Like they're so much the same, yet so different. It's really cool, actually. Yeah.